Hey guys, so we're starting Unit 6, which is laws of exponents or exponent properties. So basically what we're going to do is you're going to be taking what you know previously about exponents that you learned beginning in like 6th grade and you used last year, and you're going to be applying that to now variables with exponents. So we're going to start off with this orange notes page here. So you're going to fold it in half, and then you're going to put some tape on the back side, on this side here, and you're going to put this in your journal. So let's open this up and let's get started on, basically this is just a review. This is what do we know about exponents. So remember, an exponent is this little number at the top. So when you see a number that has an exponent, there's going to be two pieces. There's going to be a big number and then the small number. So the small number is the exponent, or you could also call it the power. So you've got your exponent or your power, and then the larger number, that's what we call the base. So a little bit of review of some vocabulary, what the two pieces mean, and we'll use these words a lot. So the base is the number that's going to be raised to the power. So we can say that. We can say this is 4 raised to the power of 2 up here. Or the exponent or power is the number of times to use the base as a factor, is what we want to say. So you have heard the word factor before. You may not remember it, but factor is when you take a number and you can multiply it by another number and get some number. For instance, we could say that 10, we could break that down as 2 times 5, right? So 2 and 5 are factors of 10. So that's basically what this is saying. It's saying to use 4 as a factor 2 times, because this is saying 4 times 4. So this is telling you how many times do you multiply this number by itself. Well, we do that 2 times. So 4 squared is really 4 times 4. And so if you want to write that in parentheses, it's the same as multiply by itself. So it's the number of times you're going to multiply it by itself. So a base that is squared is raised to a power of 2. So this has a special name. We can call this 4 squared. So 2 has a special name, squared, and then a base that is cubed is raised to a power of 3. So squared and cubed are kind of special names for exponents. Those are the ones where we can say, we don't have to say 4 to the power of 2, we can just say 4 squared. Okay, so some rules or properties really to remember here. Any number raised to the power of 1, the base is just going to stay the same. Think about it. 5 to the power of 1. How many times we multiply 5 by itself? Well, my power says to do that 1 time, so that's just 5. 2 to the 1 is still going to be 2. 1 to the 1, it's going to be 1. So anything to the power of 1 is just that number itself. It doesn't change. So that's kind of an interesting concept, because you can think of it, what if I give you the number 10? Is there an exponent written there? No, but there is still an exponent, because the only exponent that would make this still equal to 10 would be 10 to the 1. So anytime you have a number or even a variable, if there's no exponent written, we need to start thinking of it as the exponent of 1. There is an exponent or a power on every single number and variable. It's 1 if it's not written. And if it's something other than 1, it will be written. So here's a little bit of practice, and I want us to solve these instead of just using the calculator and typing these in. I want us to expand them first and see what this actually means. So 1 to the power of 5 means to use 1 as a factor or multiply by itself 5 times. So this is really 1 times 1 times 1 times 1 times 1. Did I get them all? 1, 2, 3, 4, 5. So we know that 1 times 1 is 1, and times another 1 is still 1, times another 1 is still 1, and times another 1 is still just going to be 1. So 3 to the 4th says to use 3, the base, as a factor, or multiply by itself 4 times. So this is 3 times 3 times 3 times 3. Well, we could use our calculator to solve this out. Since we know this is what it means, we know that's 3 times 3 is 9. 9 times 3 is 27. And then we have to figure out, well, what is 27 times 3. So those numbers can get pretty large. That is when you might want to come over to your calculator. Now my calculator looks a little bit different than the ones you're used to using, but it's still the same button. So do you see this little housetop button here? That's your exponent button. So you could say 3 housetop, and you see how it takes your little square up above the 3? That's for your exponent. So 3 to the power of 4 equals 81. So that would be our answer. So 27 times 3 is 81. Okay, so now we're going to look at the difference between parentheses and no parentheses. So let's look at the parentheses first, actually. Let's look at number 4. So this is saying to take -6 and square it. So it's saying to take this stuff. I don't care what's inside my parentheses. Use it as a factor or multiply by itself 2 times. So let's do that. That's -6 times -6. This stuff, I don't care what it is. Anytime you see parentheses to a power, that's what you need to think. There's some stuff inside this parentheses. I don't care what it is, but I'm going to multiply by itself how many times? This says to do it 2 times. So we know that a negative times a negative becomes a positive. And 6 times 6 is 36. So this should be positive 36. But now this piece here does not have parentheses. So this is telling us something different. Okay? This is telling us to take 6, use it as a factor 2 times, and then take the opposite of that. So you can almost think of this as -1 times 6 times 6. So that's going to be negative 36. 6 times 6 is 36. The opposite of positive 36 would be negative. So these two pieces are saying 2 different things. So we need to remember this. You've learned this before. This is something important that we're going to need to remember. So it's going to come into play a lot. So now let's look at 5 and 6. So you may notice something already between these that are similar. You see 1/2 and 2/4. So hopefully that's sticking out to you and you're saying, oh, wait a second. 1/2 and 2/4, that's the same thing. If I eat half of a pizza or if I eat 2/4 of a pizza, that's the same amount of pizza. So 1/2 and 2/4 should be equivalent fractions. So again, I have parentheses, and I see that this one is telling me to take this stuff, whatever it is in this parentheses, and multiply it by itself how many times? Well, my power is 3, so I need to multiply it 3 times. Well, my stuff happens to be the fraction 1/2. So that's what I'm going to write down. Okay, so this means 1/2 times 1/2 times 1/2. Told me to multiply that stuff by itself 3 times. So now we need to remember, okay, how do you multiply fractions? What do you actually do to multiply fractions? This may be something we've forgotten. But the rule is to multiply fractions, you multiply all the numerators, all the tops, and then you multiply the denominator straight across the bottom. So let's do that. That would end up being 1 times 1 times 1 over 2 times 2 times 2. Okay? So notice these 3 fractions multiplied actually becomes one big fraction. Well, 1 times 1 is 1, times another 1 is still 1. 2 times 2 is 4, and 4 times 2 is 8. So this ends up becoming 1/8. So that's what we need to see. So even though this is an equivalent fraction, I want us to do this one as well. But you should already be thinking, well, we should get the same answer because this is the same fraction. Maybe it's going to look like in a different form. And so I want to show you how we can take this, expand it fully, factor it out fully, and let's see what we get. So again, this one's telling me to take my stuff and multiply by itself 3 times. So let's do that. That's 2/4 times 2/4 times 2/4, which equals, now we said to multiply fractions, we multiply all the tops, the numerators, and we multiply everything in the bottom, all the denominators. 4 times 4 times 4. So I can already see that 2 times 2 is 4 and 4 times 2 is 8. That's not going to give me 1. But I want to show you what's actually happening here and how we can get exactly the same answer. So I want to expand this even further. So I want to think about 2 and 4. What do they have in common? So if I was going to simplify 2/4 to the equivalent fraction 1/2, hopefully you're thinking, well, I would divide the top, the numerator and the denominator by 2. Because 2 divided by 2 would give me the 1, and 4 divided by 2 would give me 2. So that's what I want to do. I want to separate out my 4's in the denominator, and I want to separate them into factors. So what does 4 have as factors that's common with 2? Well, that would be 2 times 2, right? So I just took this 4 and I wrote it out as 2 times 2. So now I'm going to take this 4 and I'm going to do the same thing. It's 2 times 2. And this 4, and it's 2 times 2. So now all I've done is separate my 4's into factors of 2. Okay, well look here. Think about this idea. If I have 2 divided by 2, isn't that going to just give me 1? Isn't any number divided by itself 1? Yep, it sure is. So what essentially I'm saying here is this divided by this is going to be 1, and this is where we used to cancel when you were simplifying fractions years ago in some of those early grades. So that's where we get this idea of canceling. So every 2 divided by another 2 in the denominator is going to be just 1. So 1 times any number doesn't change it, so I don't even have to write those 1's. So this fraction is going to equal what? I canceled all my 2's in the top, but there's still a 1 there. We can still say there's a 1 in the numerator. And then 2 times 2 times 2 is 8. So we did indeed get the same answer. Now we could have put this in our calculator just like this and worked it out. And it would have given us a decimal. We could have converted that decimal to a fraction. It would have been this. But I actually wanted you to see this idea of expanding this all the way as full as we can and then canceling, because this is how we're going to tackle some algebra problems that have variables, because we can't put variables in a calculator and get an answer. So these 7 and 8, look, we don't have numbers anymore. Now we have variables, but we can still use the same properties that we have been using. X to the 5th is saying to take x and multiply by itself 5 times. So that's x times x times x times x times x. That's all it's saying. Now I don't know what x equals, so I can't take this any further. I can't put this in my calculator because I have to know what the value of x is, and it didn't tell me. But I do know that these two statements here are equivalent. They're equal to each other because that is what exponents mean. It means to take something and multiply by itself however many times the exponent tells you to. So it's the same thing with a. This is a to the 4th, so it's going to be a times itself 4 times. So I wanted us to see that with exponents. So now 9 and 10 says, take the expanded form we've given you and take it back to the exponential form. So I look and I see I have 11. So right off we should see that 11 is our base. That's the number that's being multiplied by itself. And how many times? 1, 2, 3, 4, 5. So my power should be 11 to the 5th. Now in number 10, I have negative 5 as a base, right? And it's multiplied by itself 1, 2, 3 times. So I know there's a power of 3. But now we need to think about this for a second, because this is what we are tempted to write. But go back up here and remember that if you have negative 6 squared without parentheses, it's saying to take your base, multiply it, and then take the opposite. But with parentheses means that you multiply the negative that many times as well. So this one, every single one of these pieces has a negative. So I need to put parentheses around this, because this is saying to take negative 5, multiply times itself 3 times. So we have to be careful when we're writing these parentheses. So this is a short little review of what hopefully you do remember about exponents. And then next we're going to look at a new type of exponent that you haven't seen yet, but hopefully we'll make a little bit of sense of it when we talk about zero exponents.